I want to work through an example problem of 1D particle motion, which will allow us to kind of look at how we might evaluate something of this nature. So in this example problem, we have a ball that is being tossed in the air from a platform that is at a height of 10 meters. I guess it's a pretty tall platform. And the ball is being thrown, and at the time point that we're looking at, it is at a height of 10 meters and traveling upwards with a velocity of 10 meters per second. So we have a lot of repetition in our numbers here. And the things that we want to find are functions that would represent the position and the velocity of this ball with respect to time, how high the ball will eventually get before it stops and starts coming back down, and when the ball will hit the ground. So what time will that occur? So to start this problem, we need to kind of think about, like, what do we know about this situation? We might say we know some initial conditions, right? So we know the initial height when time equals 0 is 20 meters. So this is the height of the platform plus the height that the ball is at from the platform at the time point that we're looking at, the initial time point. We know the velocity of the ball at this initial time step is given as 10 meters per second. And the other bit of information that we know that isn't represented in our figure up here is that the ball is going to be slowing down and eventually falling back to the earth, and that is due to the acceleration of gravity acting on the ball, the force of gravity resulting in an acceleration. So we know that our acceleration is 9.81 meters per second squared. But the only thing we have to be careful about is that acceleration is acting in a downward direction. G is our acceleration, gravity, often written with the letter G. Acceleration of gravity is acting in a downward direction. We've defined our coordinate system with a y-axis pointing up, so we need to make sure we include a negative sign on our acceleration here. Great. So we can start evaluating this problem. And we want to ultimately arrive at some functions which represent position and velocity for part A. So we can go ahead and say, well, our acceleration is equal to minus 9.81 meters per second squared. And we know that acceleration is also equal to dv by dt. So that's useful for us. We can take this as a differential expression and start to solve stuff with it. So to do that, I'm going to take my dt and move that over to the right-hand side of my equation such that I get dv equals negative 9.81 dt. I'm leaving my units off here just for simplicity of writing it. And this is basically separating the variables. And we know that if we have a differential expression like this, mathematically we can take an integral of it, of each side, in order to evaluate this. So I can go ahead and integrate the left-hand side. I can integrate the right-hand side. And for integration, we need to know our limits. So we know our initial velocity, since this first left-hand side integration is with respect to velocity. We know our initial velocity at time 0 is 10, and we don't know our eventual velocity, so we'll write that as v with respect to time, or as a function of time. On the right-hand side, we're differentiating with respect to time, dt. We're going to call our initial position time 0, and we don't know our end position or our end time, so we'll just call that t. So the left-hand side, the integral of dv with respect to v is just v. And on the right-hand side, the integration of negative 9.81, that's just a constant, move that out front. So the integration of dt with respect to t is just t. Now we have to bring our limits in here, so we're going to evaluate each of these from their with respect to their limits. I'm writing this by just putting brackets around and then providing the lower and upper limits. And if you recall from calculus, when you evaluate this sort of integral over its limits, you plug in the top and then minus the lower limit. So I would end up with Vt minus 10 equals negative 9.81 t. 0, of course, drops off. All right, so I have this expression. For simplicity, I'm going to move the 10 over, so I end up with negative 9.81 t plus 10. Now this looks like a nice expression for velocity in terms of time, and that's what we were aiming for. Next, we're looking for an equation for position. So we can treat this in the exact same way by realizing that v is just dy by dt, carrying my expression down, negative 9.81 t plus 10, that stays the same. Now I can do the exact same thing, separate my variables by moving dt over, and I get dy equals negative 9.81 t plus 10 times dt. Now, once again, I can integrate both sides, and I need to figure out what my limits are. Well, up in the problem statement, we said that our initial position of y was 20. So we can go ahead and plug that in just like we did in the last part. And we don't know necessarily our end position, so we'll plug that in as a function, y of t. And do the same thing on time. We know our initial time is 0 and our end time is t, because we don't know what the end time is. So if we carry this out in the same way, we get y evaluated from 20 to y, and we get the integration. Now we have a function of t, so when we take the integral with respect to t, we get 1/2 t squared. So 1/2 of 9.81 is about 4.9, remembering my negative sign, t squared. The integration of 10 with respect to t is 10t. And all of this needs to be evaluated from 0 to t. All right. Carrying this through, we get y of t minus 20 equals negative 4.9 t squared plus 10t. And finally, y of t equals negative 4.9 t squared plus 10t plus 20. So that gives us a nice expression, mathematical expression for position with respect to time. All right. So the next question is, how high will the ball get? And to evaluate this, we need to think about like what this means. So how high will the ball get? Well, if you've ever tossed a ball in the air and thought carefully about it. As you toss the ball in the air, right, it travels up with some velocity, it stalls out at the top before it comes back down, right? So what is the defining characteristic of that condition? Well, the defining characteristic is that when the ball stalls out at the top, its velocity is 0. So we can use that as the condition that we are going to apply in order to evaluate this problem. So for part B, we'll say the condition is that velocity is equal to 0. So to evaluate this problem, we can come back and look at what we have here that we've solved for in part A. We have equations for velocity and we have equations for position. Ultimately, we're trying to find how high the ball will get, which is position, y. But we don't have a function or an equation for y in terms of velocity. But what we do have is a function for y in terms of time, and we have a function for velocity in terms of time. So those are our two equations. So what we can do is go ahead and evaluate our velocity equation, which is negative 9.81t plus 10. And this expression now has only one variable in it, and that's t. So we can use this expression. We'll add the 9.81t over to the left-hand side. So we get 9.81t equals 10. Divide the 9.81 across, and we get t equals 1.019 seconds. So we know when the velocity of the ball will go to 0. It'll go to 0 just over 1 second after we throw it. Now we want to find out where that occurs. So to do that, we can take our expression for y, set t equal to 1.019 seconds, and evaluate it. So we have negative 4.9 times 1.019 squared plus 10 times 1.019 plus 20. So if we go ahead and evaluate that expression, plugging it into our calculator, we get a position of 25.1 meters. And this is measured from the ground. So after this ball leaves our hand, gets to the position we know its velocity at, which is 10 meters up above the platform, it'll travel another 5 meters from that point before stalling and starting its path back to the ground. All right, the third question then is when will it hit the ground? So again, we want to think about what is the condition of this situation. The condition that you've hopefully set in your heads or thought about is that the position at the time when it hits the ground is going to be equal to 0. So we've defined ground as 0, and therefore that's the case that has to happen. So we have a function for y, and I'm going to write it again, negative 4.9t squared plus 10t plus 20. And we're looking for the time at which this function is equal to 0. So you can see we have a quadratic expression here. We can go ahead and solve that by plugging it in to our quadratic equation. So as a point of reminder, I need to give myself some more screen space here. As a point of reminder, the the quadratic formula is of the form x equals minus b plus or minus the root b squared minus 4ac over 2a. And this is when your function is of the form ax squared plus bx plus c equals 0. Oops. So we can evaluate this quadratic formula to solve for t by plugging in all of our values. In this case, we have a, b, and c that we would plug into this formula. So we have minus 10 plus or minus square root of 10 squared plus 4 times 4.9. This minus became a plus because of the negative 4.9 times 20, all divided by 2 times negative 4.9. Now, there's a plus or minus that you note in here, which means there's two answers to this equation. So if you solve this, plug it into your calculator like I did, you come up with two possible answers, one being 3.28 and the other being negative 1.24. Of course, the negative number, or the negative answer, doesn't really make sense because we're not going back in time. So for our purposes, only the positive answer makes sense, and we get that the time at which the ball strikes the ground after the initial point that we defined would be 3.28 seconds later. Now, for fun, we can also evaluate, well, what is the velocity at this time, 3.28 seconds. And we can plug it into our velocity equation. And we end up finding that the velocity when it strikes the ground is 22.19 meters per second. Negative, which means it's traveling downward. All right, thank you.